Good afternoon. Welcome to the Diesel Technology Forum's webinar, Powering the Future, Trends Shaping the Use of Diesel Power Generation. During the presentation, all participants will be in the listen-only mode. As a reminder, this event is being recorded. To ask a question at any time during the event, submit the question via the chat Q&A box. We encourage you to ask questions at any time during the presentation. Your questions will not be viewable by other attendees and will be addressed during the Q&A at the end of the session. I would now like to turn the call over to your moderator for today, the Diesel Technology Forum's Director of Policy, Dawn Fenton.
Thank you, Kristen, and thank you to everybody who's with us today. This is the second of two webinars we are hosting on diesel power generation. Our initial webinar was held on Tuesday this past week, where we had speakers addressing issues such as the various uses of diesel generators across different industry sectors. We talked about the technology advances in diesel generators, and we also had a speaker talking about the use of diesel generators in demand response programs. Today we have another great panel of speakers with us who will be talking about current and then future regulations on the diesel power generation sector, as well as a comparison of diesel and natural gas generators, including the attributes and benefits of each. Well, I'm sure many of you are familiar with the Diesel Technology Forum, and I'm sure several of you were on our panel, on our webinar earlier this week. For those of you who are not familiar with our organization, the Diesel Technology Forum is a nonprofit educational trade association that works to increase awareness about clean diesel technology. Our membership includes companies across all segments of the diesel industry, and we undertake a variety of programs and activities to inform policymakers, the media, and equipment users about technology advances and the industry's contribution to a clean energy economy. In addition to hosting webinars such as this one, we conduct a variety of technology demonstrations and policy briefings and have a range of educational materials on our website. For those of you who are interested in learning more about the Diesel Technology Forum, I encourage you to visit our website at www.dieselforum.org. In terms of today's webinar, after we hear from each of our three speakers, you will have an opportunity to hear their answers to questions that you have. I invite you to submit written questions throughout the session during their presentations, after which I'll read as many as I can for the benefit of all participants. I want to also reiterate what Kristen mentioned, reminding everybody that today's webinar is being recorded, so you'll have an opportunity both to download presentations in the future, or you could even listen to the entire recorded session, as well, including the Q&A portion, within a day or two after the event by visiting our website. With that, I'd like to introduce our first speaker for today, who is Melanie King. And Melanie is an environmental engineer with the U.S. EPA Office of Air Quality Planning and Standards within the Energy Strategies Group. She is responsible for developing regulatory and other programs aimed at reducing criteria and air toxic pollutants from stationary combustion sources. She's currently working on implementing regulations for stationary internal combustion engines under Sections 111 and 112 of the Clean Air Act. Prior to joining EPA, she worked for the North Carolina Department of Environment and Natural Resources in the Division of Air Quality, as well as for a consulting firm where she worked with EPA on the development of NESHAP and the NSPS. So with that, Melanie, thanks so much for being with us today, and we look forward to your presentation.
Thank you, Dawn. I'm going to give an overview of the National Emission Standards for Hazardous Air Pollutants for Stationary Reciprocating Internal Combustion Engines. It's a lot of acronyms. This is in the CFR. This is Part 63, Subpart ZZZZ. We also call it Quad Z. The affected source under this rule is stationary reciprocating internal combustion engines, or RICE, at both major and area sources of HAPs. And what do I mean by a major source or an area source? A major source is one that emits 10 tons or more per year of a single HAP, or 25 tons or more per year of combined HAPs. And it's the whole facility, so even if it might be the engine and then other emission sources at the facility. And I just want folks to understand that the engine's either going to be at a major source or an area source. An area source is any source that's not a major source. So if it's not a major source, it's automatically an area source. So even a single engine by itself is an area source. I get the question a lot, what do we mean by stationary? We define it as not used in a motor vehicle and not a non-road engine. And a non-road engine is one that's self-propelled, propelled while performing its function, or it's portable or transportable, meaning it has a handle, it's on wheels, it's on a trailer. But it's important to note that under that portable qualification, if it stays in the same location for more than 12 months, it does become a stationary engine under these rules. And there's two terms that you'll hear me use, compression ignition or CI, which is basically diesel engines, and then spark ignition or SI, which is basically gas-fired engines. And we within the rule, we break engines down into CI or SI. So when you see those acronyms, that's what I'm referring to. So I just want to give a little sort of overview of the history of the rule. It was first promulgated back in 2004, and that action covered engines that were greater than 500 horsepower and at major sources of HAP. Both existing engines and new engines that came online. Then we amended the rule in 2008 to cover engines that were less than 500 horsepower and at a major source and were new, so were constructed after the rule was implemented, and then engines of any size at area sources that were new. So what we've done this year is finally sort of complete the whole pie and regulated the remaining sources, which were the existing engines that were less than 500 horsepower at major sources and existing engines of any size at area sources. And we also added new standards for existing engines that were greater than 500 horsepower at major sources that were non-emergency CI engines. What I'm going to focus on today is just the requirements for CI engines under these 2010 amendments. And I'll just, on the next slide, give a little overview. The amendments were done in two parts. On March 3rd, we promulgated the amendments for the existing CI engines. On August 20th, we promulgated the amendments for existing SI engines. What do I mean by existing? For the engines that are less than 500 horsepower located at a major source or any size located at an area source, existing means constructed before June 12, 2006. For the non-emergency CI engines greater than 500 horsepower at a major source, existing means constructed before December 19, 2002. And one thing I did want to note that under these amendments, existing emergency engines at area sources that are residential, institutional, or commercial facilities are not covered by the amendments. So, like I said, I'm going to focus on the requirements for CI engines, and so this next slide here shows what the applicable emission standards are. For major sources, the engines that are less than 100 horsepower, or also the emergency engines and black start engines, which means engines used to start up a turbine, they have work practice standards, which I'll talk about a little bit more. They're basically maintenance requirements. For the engines 100 to 300 horsepower at major sources, they have a 230 parts per million CO limit. And then the 300 to 500 have a 49 ppm CO or 70% reduction. And then greater than 500, it's 23 ppm CO or 70% reduction. And the reason those two cells are highlighted in yellow is is because the basis for setting those limits was engines that are equipped with an oxidation catalyst. So those are the size engines that we anticipate will need to be retrofit with a catalyst in order to meet those standards. So it's basically the non-emergency engines greater than 300 horsepower. Same thing for the area sources. You'll see the same emission limits for the greater than 300 horsepower engines. The rest of the engines at area sources have management practice standards, which they're basically the same thing as the work practice standards. It's really a terminology thing, and they are maintenance requirements. One thing I did want to point out for area sources, there's engines greater than 300 horsepower non-emergency. Those CO limits do not apply to engines located in rural Alaska. They have management practices as well for those engines. What is an emergency engine? That's the next slide. We define it as, it's used an unlimited amount of time for emergency service. So if, like say an ice storm, that's a good example for today, hit and your power was out for a week, you could run it, for all that time that your power was out, and, there's no limit on that. Maintenance checks and readiness testing is limited to 100 hours per year. And part of that 100 hours, the rule says you could use 50 hours for non-emergency purposes, but that cannot include peak shaving or any kind of operation as part of a financial arrangement with another entity, except that 15 of those 50 hours can be used for emergency demand response, for example, an imminent blackout. I'm going to talk a little bit about the compliance requirements. For the non-emergency existing CI engines that are greater than 300 horsepower, they have to use ultra-low sulfur diesel fuel, and they have to install crankcase emission control requirements. The ULSD requirement does not apply in rural Alaska. The engines with numeric CO limits, which are basically those greater than 100 horsepower non-emergency at major sources, and greater than 300 horsepower non-emergency at area sources, they have to do an initial performance test to show compliance with the emission standard. Then they would have to do subsequent testing every 87, 60 hours or 3 years if they're larger than 500 horsepower. That interval can be extended to 5 years if the engines are defined as limited use, which is used less than 100 hours per year. And then if they're greater than 500 horsepower, they also have to continuously monitor their catalyst inlet temperature and do monthly checks of their catalyst pressure drop to make sure that they're within operating limitations specified in the rule. In terms of those work and management practices, they're basically change the oil and filter, inspect the air cleaner, hoses, and belts on a prescribed schedule. So it's like every, 500 hours or 1,000 hours or something like that, depending on the size and the application. You also have to operate and maintain the engine and the control device per the manufacturer's instructions, or you have to develop your own maintenance plan. You can use an oil analysis program to extend the frequency for doing those oil changes. So, say your frequency is every 1,000 hours, then once that 1,000 hours hits, you could do an oil analysis program. And if the oil parameters are within what's specified in the rule, then you can extend the oil change frequency. And also for emergency engines, they have to have an hour meter. In terms of the notifications and the record keeping and reporting that's required, those engines that are subject to a numeric CO limit or a % reduction requirement have to submit the traditional notifications, such as like an initial notification and notification of performance test. And they also have to submit semi-annual compliance reports. If you're an emergency engine, you don't have to submit any notifications, but you do have to record hours of operation. And then those engines that are subject to the worker management practices, the ones that don't have a numeric CO limit, they have to keep records of the maintenance conducted on the engine. I wanted to mention the startup, shutdown, and malfunction requirements. There was previously the way the rule was laid out, it said that deviations that occurred during startup, shutdown, and malfunctions would not be considered violations. And that was consistent among several NESHAP rules, not just this one. And there was a court decision that came down in, I believe it was late 2008, that said that basically threw out that exemption. So in response to that court decision, we amended the rule, and now it says that the emission standards that apply during normal operation also apply during shutdown and malfunction. So that, 43 ppm CO limit, for example, that would apply during the shutdown of the engine and any malfunctions. For startup, we specified that the startup and the idling time must be kept to 30 minutes or less. And this also applies to engines that were covered by the previous two amendments to the rule. And we did take out the requirement that the engine have a startup, shutdown, and malfunction plan. So just wanted to mention some key dates. The engines that were already subject to the rule, which would be those covered by the 2008 and 2004 rules, they had to start complying with those startup, shutdown, and malfunction limits once the effective date of the rule passed, which was May 3rd of 2010. For the existing diesel engines, the compliance date is going to be May 3rd, 2013. So that's the date by which they would have to start complying with the emission limits and the ULSD requirements and the crankcase controls, that kind of thing. And just wanted to mention for existing SI engines, the compliance date is going to be October 19th, 2013. In terms of the next steps, we did get a petition for reconsideration of that allowance for 15 hours for emergency demand response for emergency engines. We got petitions from a couple of different groups. So we did grant reconsideration on that issue, and we actually published a notice in the Federal Register last week, December 7th specifically, just to let folks know that we did grant that reconsideration and that we do plan to have a public hearing, or actually meeting, I guess we're calling it. So if anyone's interested in participating, it's going to be on January 13th. The notice says it's going to be January 6th, I believe, but we actually had to move it to January 13th. So we're going to be putting out another notice. We did receive some additional petitions on the SI final rule, petitions for reconsideration, and also judicial review. We haven't made any decisions yet about whether we want to grant those petitions or not. We have been putting together some implementation materials to try to help folks figure out, what do I have to do to comply with this rule. So I put the link there to where those materials are. We're trying to develop some additional ones. So, we may be posting new ones once we get them developed. And then I did want to mention one other next step. We have another regulation that applies to diesel engines, which is the new source performance standard. It's in Part 60, subpart 4I. And we did propose some amendments to that rule back in June of this year, and we will be finalizing those amendments early next year, probably in the spring. So there is another action coming up that would affect diesel engines. And if anybody needs more information about that, just let me know. And then the last page is just my contact information. If anybody has any questions that they didn't even want to bring up now, but they're, later on, feel free to give me a call or send me an email.
Great, Melanie. Well, thank you so much for that presentation. It was a great overview and of what's a very complex regulation, and I'm sure you'll be getting additional questions. There are already some folks have sent some in, submitted some, and that we'll get to at the end of all the presentations. And you noted, Melanie, that you guys are putting together some additional materials to help folks in the field. I want to mention also that the Diesel Technology Forum has put together kind of a two-page summary of the rule, and that is available on our website. And we can be sure in a follow-up email to all registrants that we provide a link to that document, although certainly you can just go on your own and pull it up. So it's a piece that just summarizes the NESHAP for rice roll. So thank you very much for that, and we'll move on to our next speaker, who is Mark Prettyman. And Mark has been an environmental scientist with Delaware's Division of Air Quality for nearly 9 years. As a member of the Airshed Evaluation and Planning Group, Mark has led the development of regulations pertaining to the control of emissions from stationary generators, combustion turbines, and coordinated the first of a state adoption of the Federal Outer Continental Shelf regulations. Since 2004, he has been leading Delaware's efforts to control emissions from stationary generators and provides compliance assistance to all generator owners in Delaware, as well as providing assistance to surrounding states in their development of generator regulations. Mark assists with the development of Delaware's emission inventories for non-point sources and helps the Division of Air Quality staff with data management and quality assurance for the state's state implementation plans related to ozone, regional haze, and fine particulate matter. So with that, Mark, thanks so much for joining us today, and we look forward to your presentation on the Ozone Transport Commission's model rule.
Great. Thank you, Dawn. Hi, everyone. Today I'll be talking with you about the Ozone Transport Commission's model rule for stationary generators. First, I'd like to briefly discuss the Ozone Transport Commission. Next, I'll have a short discussion of the National Ambient Air Quality Standards for ground-level ozone. And finally, I'll have a discussion on the model rule for stationary generators and its requirements. First of all, what is the OTC? The Ozone Transport Commission, or OTC as it's known, is a multi-state organization that was created under the Clean Air Act. The OTC brings together the states from Virginia to Maine to coordinate reductions in air pollution that benefit the whole region. It is responsible for advising EPA on transport issues and for developing and implementing regional solutions to the ground-level ozone problem in the Northeast and Mid-Atlantic regions. In addition to addressing ozone, the OTC considers precursor pollutants as well as co-benefits from the reduction of non-ozone pollutants in its reduction strategies. The OTC is actually not unique, since in fact there are similar agencies across the country. The 6 New England states, New York and New Jersey, are part of a non-profit association known as NESHAP, which stands for the Northeast States for Coordinated Air Use Management, which provides support to the air quality and climate programs of its member states. Similarly, the Visibility Improvement State and Tribal Association of the Southeast, or VISTAS, is a collaborative effort of state and tribal governments associated with the management of regional haze, visibility, and air quality issues in the southeastern United States. As for the structure and process of the OTC, it is comprised of different committees, such as those for mobile sources, modeling, and stationary and area sources. State representatives participate in each committee and help to form focus groups and work groups on varying strategies and regional issues. Stakeholders are a key part of any strategy as well, and meetings and conference calls are held to offer stakeholders an opportunity to comment on the OTC measures and current ozone-related policy topics. Typical end products of the OTC committees may include a Memorandum of Understanding, or MOU, which details cooperative actions among states, or a resolution which is an action or approval of an OTC measure. While these OTC actions are not binding to industries or states, they do carry significant weight in affecting subsequent federal or state policy regulations which could be binding. Many successful air quality programs have come out of the OTC, such as its MOU to develop a regional strategy to control stationary sources of nitrogen oxide. The OTC's NOx budget program, which was an allowance trading system designed to reduce summertime NOx emissions, helped to reduce NOx in the OTC region by 60% from its 1990 baseline emissions. The OTC has also been successful in the creation of various model rules which OTC states have already adopted to help reduce emissions in their states. Slide 6. As for ozone itself, it is a pollutant which is regulated by the EPA as a national ambient air quality standard in order to protect public health and welfare, including protection against decreased visibility and damage to animals, crops, vegetation, and buildings. An initial 1-hour standard was set in 1979 at 0.12 parts per million. An 8-hour standard was then set at 0.08 parts per million in 1997 and updated to 0.075 parts per million in 2008. So this update is currently being reconsidered. As for the 0.08 standard, all OTC states have submitted state implementation plans to the EPA, which include state regulations and other technical details in order for a state to meet the ozone standard. But these steps the approval status for these SIPs are all still pending. The New York and Philadelphia non-attainment areas will most likely attain the 0.08 part per million standard, but it's possible that the Baltimore non-attainment area may not. This past January, EPA decided to reconsider the 0.075 parts per million standard and reduce it to the range between 0.06 and 0.07 parts per million. Many OTC states would already be considered non-attainment for the 0.075 parts per million standard, so lowering it would even be more of a challenge to attain. Although this updated 8-hour standard was supposed to be released by the end of the year, the EPA has recently announced a delay in the final issuance of the 8-hour ozone standard until no later than July 31st, 2011. States which are classified as non-attainment for the new standard will need to attain between 2016 and 2027, depending on how high above the standard their air quality actually is. The images you see on this next slide are just to show a quick comparison of the current standard compared to the proposed standard. Both images represent the 8-hour ozone design value for the OTC region, which is an average of the 2008, 2009, and 2010 data. The image on the left shows that most areas in the OTC region are attaining the 0.08 part per million ozone standard. The image on the right shows that areas of Delaware, New Jersey, Pennsylvania, and New York would probably be just above the 0.075 parts per million standard, represented by the orange color. But a much wider region would be classified as non-attainment if looking at a range between the 0.06 and 0.07 parts per million, which includes the areas colored in yellow, green, and dark green on the image. As the previous slide alludes to, in order to attain the new ozone standards under consideration, OTC states will need further emission reductions from the ozone precursors of nitrogen oxides and volatile organic compounds. To add to this challenge, transport of ozone and its precursor compounds from upwind states will continue to contribute to OTC states' non-attainment of these new ozone standards. As for what sort of controls will be needed and looked at for emission reductions, many of the typical low-hanging or mid-hanging fruit are gone, and reductions from non-traditional areas will have to be sought out. As an estimate, the EPA has suggested that the OTC region alone would need another 40% reductions in order to meet the proposed standard, while other areas like the Midwest may need even more. Slide 10. Over the last couple of years, the OTC Stationary and Area Source Committee has looked into a wide range of proposed control measures, as you can see from the list on this slide. These measures have been categorized as either NOx controls or VOC controls. One such source of potential NOx reductions could be attained from stationary generators. OTC states have struggled with ozone non-attainment since the 1-hour standard was set back in 1979. Although there have been big ozone reduction benefits from the regulation of NOx sources, many stationary generators have gone uncontrolled due to the relatively small size compared to typical thresholds at which other stationary sources are regulated. While the EPA's non-road rules and the new source performance standards have been a good start at controlling the emissions from engines, the episodic nature of the OTC region's ozone problem and the episodic nature of a stationary generator's use dictate a closer look at reducing the emissions from stationary generators. Because ozone is episodic, daily emissions are a concern, and for a generator, its daily emissions can be significant even if its annual emissions are small. Additionally, there is more interest than ever in using generators for other purposes, other than just for power outages, such as demand response and peak shaving. The additional emissions from these types of non-emergency use can be detrimental to air quality. Thus, the OTC formed a work group to look into the potential model rule for stationary generators. After nearly 2 years of a discussion and analysis by state regulators and stakeholder groups, the OTC has developed such a model rule, which states can use at their discretion to help control emissions from stationary generators. The model rule will help to ensure that emissions from stationary generators are controlled, especially when they are used for non-emergency purposes, while not hindering their use as they were originally intended, which is to provide emergency backup power. The model rule initially began as an update to the Ozone Transport Commission's model rule for additional NOx control measures. but it was tailored to specifically apply to stationary generators powered by internal combustion engines, but it specifically exempts combustion turbines from its requirements. The model rule includes a low-end cutoff between 10 and 100 kilowatts, which states may decide at their discretion, but it does not include a high-end cutoff. Based upon stakeholder comments and review, the model rule does also include exclusions for emergency generators used at nuclear power plants subject to Nuclear Regulatory Commission regulations, as well as engines used by the United States Navy for testing or training purposes. The following few slides discuss some of the key definitions which are important to the structure of the model rule. In order to have a model rule for stationary generators, the term generator must be adequately defined. The OTC model rule defines a generator as an internal combustion engine, except for a combustion turbine, and associated equipment that converts fuel to electricity or to electricity and thermal energy. The definition of emergency is also key to its classification to a generator, since it can determine if the generator will be subject to more or less stringent requirements. The OTC model rule defines an emergency as a power outage or a deviation of voltage or frequency from the electrical provided. The definition includes an optional section which would allow an individual state to add a provision allowing a generator to operate in conjunction with a state's respective independent system operator for emergency purposes. Ideally, the independent system operator would implement a voltage or frequency reduction, which would then allow the emergency generator to participate in any emergency demand response program which the independent system operator has. As the two individual definitions on the previous slide suggest, an emergency generator can only operate during emergencies, but it can also operate for testing and maintenance purposes as well. A non-emergency generator may operate at any time, including emergencies, testing and maintenance, as well as any other time it wishes. Different requirements of the model rule will apply to different generators depending on when they are installed, which is why definitions of new or existing have been included in the model rule. These terms are used to define a generator which is installed or repowered after the effective date of the regulation, once a state adopts the model rule, of course, as new. A generator which is installed prior to the effective date of the regulation would be classified as existing. Since the model rule will only apply to stationary generators, it is imperative to define stationary. The model rule defines stationary as a generator powered by an engine which is not a non-road engine, as this term is defined in 40 CFR 89.2. Since the federal definition of a non-road engine incorporates different provisions of what a non-road engine is, the model rule simply references the federal definition in order to capture these nuances. Thus, stationary refers to a generator which has a 12-month residence time or shorter or seasonal, are not portable or transportable, and are not propelled or intended to be propelled. Outside of any sort of permitting that a state may require, the model rule includes an initial notification to be sent to the state for each and every generator in the state as a sort of registration. Most states do not have a detailed data on the number of generators in the state, whether they're operating for emergency or non-emergency purposes, or the overall capacity of all the generators in the state. By requesting this information, data can be used to evaluate the effectiveness of the regulation which the state may adopt and aid in estimating emissions reductions in a particular state. Basically, the requirement states that a generator owner would submit to the state specific information for each of the generators owned, which includes the generator owner's name and address, the make, model, year, and physical address of the generator, as well as a classification of whether the generator is being used for non-emergency or emergency purposes. Slide 17. One very important part of the OTC model rule are the emission standards which would apply to stationary generators. This slide shows that the emission standards are broken into 4 categories based upon whether the generator is classified as either new or existing, or is used for emergency or non-emergency purposes. Under the model rule, an existing emergency generator does not have a specific numerical emission standard with which to comply, but they must follow manufacturer's maintenance and operating requirements to help minimize emissions. Alternatively, a new emergency generator must meet the applicable emission standards set by the US EPA and the new source performance standards for either compression ignition or spark-ignited engines. This slide shows that the emission standards which would apply to existing non-emergency generators under the model rule. The standards are shown in both pounds per megawatt hour and equivalent gram per kilowatt hour units for comparison purposes, since most emission standards set by the EPA for engines are displayed as grams per kilowatt hours. One thing to note with these standards is that they equate to an approximate 90% reduction in emissions from an uncontrolled diesel generator. The state of Delaware is utilizing these standards, and they are currently being met by existing non-emergency generators operating in the state. Another thing to note is that the reciprocating internal combustion engine NESHAP, which may require more stringent CO standards, as Melanie discussed earlier, than those proposed in the model rule. The current slide shows the emission standards which would apply to new non-emergency generators under the model rule. And again, these standards are represented as pounds per megawatt hour and gram per kilowatt hours for comparison purposes. The standards equate to the most stringent Tier 4 standards of the non-road rules. Although the Tier 4 standards do not take effect until 2014, which is a full 3 years away, the standards are included in the model rule to allow a 3-year time frame for the state to consider adopting the model rule, go through a regulatory development process, and allow adequate time for implementation. The current slide shows the emission standards of the model rule which apply to new non-emergency generators which are fired by waste, landfill, or digester gases. These standards have been recommended by the Engine Manufacturers Association and are currently being met by numerous landfill gas-fired generators operating in the state of Delaware for non-emergency purposes. In regards to operating requirements for stationary generators within the model rule, it does not include restrictions on the number of hours a generator may operate. Instead, the model rule just states that an emergency generator can only operate for emergencies or testing or maintenance. However, an emergency generator cannot operate for testing on a day which has been classified by the state or local air quality agency as unhealthy for sensitive groups or greater on the US EPA Air Quality Index. Alternatively, a non-emergency generator would not be restricted in its hour of operation or when it may operate. Although the model rule would not impose operating hour limitations on a stationary generator, a state or local air quality agency could require operating hour restrictions as part of an approved operating permit. The model rule does include other various requirements such as fuel sulfur content limit and record keeping. If a state were to adopt the rule, it would require all shipments of diesel fuel that are received for use in a diesel-fired stationary generator to have a sulfur content of 0.0015% or 15 parts per million, which is also typically known as ultra-low sulfur diesel fuel. As for record keeping, the model rule requires monthly and yearly records for fuel usage, operating hours, and hours when testing and maintenance are performed. Additionally, a non-resettable hour meter is required to be installed on a stationary generator, which makes it very easy to determine the monthly operating hours. Most, if not all, new generators include a non-resettable hour meter installed by the manufacturer. The model rule also requires all records to be kept for 5 years, and they can be kept as either hard copies or electronic. Model rule also includes an optional requirement which a state may choose to adopt if it wishes. This optional record-keeping requirement would require all non-emergency generators to submit all of their records for a calendar year to the state at the end of each year. To aid stationary generator owners in achieving their applicable emission rates, the model rule includes an optional section which would allow a generator to take credit for certain emission reductions. For example, if a stationary generator were to operate on a gas that would otherwise be flared, such as landfill gas, the emissions that would have been produced through the flaring could be deducted from the actual emissions of the generator. If a stationary generator were operating as a combined heat and power system where the thermal energy is used in addition to the electrical energy generated, the generator could then also receive a compliance credit against its actual emissions. Additionally, a stationary generator can receive another credit if a non-emitting resource, such as a solar array or wind turbine, is operating simultaneously to generating electricity. And with that, that concludes my presentation of the OTC and its model rule to control the emissions of stationary generators. Thank you very much for your time.
Thanks very much, Mark. That was a great overview of both the OTC and the model rule. So before I introduce our next speaker, I just want to remind folks of a couple of things. First of all, that this whole session is being recorded, and the recorded version will be available online. And you will also be able to download all of today's presentation, so no need to have to copy down the content of the slides that you're seeing. Second of all, I'd like to remind folks to please feel free to submit any questions for our speakers in the Q&A box that you see on your screen. We have had several that are coming in, and would encourage you to do that even as Wissam is speaking here, and then we will take these all at the conclusion of his presentation. With that, let me introduce Wissam Balshi with Cummins. He serves as an application engineering team leader at Cummins Power Generation. Wissam joined Cummins in 2007 and serves as the point of contact for questions on generator set sizing, codes and standards, power systems, and general standby application considerations. He attended the University of Minnesota, where he received his bachelor's in electrical engineering, and he's been working since then with Cummins in a variety of application engineering positions, mainly designing standby power systems such as uninterruptible power supply systems and generator sets. And Wissam is going to talk to us today about looking at both diesel and natural gas generators and highlighting the different attributes of each. Wissam, thanks so much for your time and being here with us today.
Thank you, Don. I'm going to be focusing mainly my discussion on diesel and natural gas generator sets for commercial and industrial applications. We're going to talk about the capabilities of the different prime movers used for the generators, and end with market trends and future expectations for diesel generator sets. So with that, we'll go into the selection considerations that go into selecting the fuel type for your prime mover. For industrial and commercial applications, we mainly use reciprocating internal combustion diesel and natural gas gensets. And there are a few factors that go into selecting that prime mover. Mainly, we're going to talk about isolated bus performance. And when we talk about isolated bus performance, for those who are not power systems engineers, we're mainly talking about a situation where a generator or a group of generators are feeding the load in a situation where you're not running in parallel with utility grid, where frequency stability is important. The other thing we're going to have to consider is the life cycle cost. Life expectancy of diesel and natural gas generators are different. How often do you need to maintain it, and the capital and operational costs are different, so we have to consider that when selecting the fuel type for the prime mover. The duty cycle is very important. Understanding whether it's going to go into a standby application, a prime application, or a continuous duty application will determine what fuel type you need for your application. When we talk about standby, it could be emergency standby, or it could be optional standby. When we say prime, we're talking mainly in situations where you don't have a reliable grid, where your generator is the prime source of power, or it could also apply to peak shaving applications and base loading type applications. The reliability and availability of the generator and how often you need to maintain it and replace the serviceable components on it, oil change, filters, all that. That also goes into the consideration for the fuel type. And we'll also talk a little bit about the exhaust emissions output of the different prime movers. And we'll end with market trends. So when we're talking about diesel generators, there are a few benefits and advantages for diesel. The main point is really that compression, ignition, or diesel engines have the highest torque developing capabilities of all internal combustion engines. This is why you see diesel being used in many industrial and commercial applications. When used as a prime mover for generating electricity, it will generally have better load acceptance and transient performance than any other prime mover. This high torque capability of the diesel engine is what makes it the main selling point for using it in standby applications. Load acceptance is very important. Recovering from the load acceptance to nominal voltage and frequency within 10 seconds or 60 seconds, depending on the type of load, is very important. And with diesel engines, you can accept load much better than a natural gas generator would. Frequency stability in steady-state operation is also very important. This is especially important nowadays with the increased use of nonlinear or rectifier-based loads, such as those used in data centers, uninterruptible power supply systems, telecommunication applications, basically applications where you're converting AC to DC. The frequency needs to be stable, and diesel has better frequency stability in steady-state operation than natural gas. The other thing is thermal efficiency of the power supply system. Modern high-performance diesel engines equipped with exhaust gas turbochargers and intercoolers have a thermal efficiency, which is electrical output per unit fuel input, of about 40%. This is higher than natural gas or spark-ignited gensets, where you have basically your thermal efficiency running at about 30 to 33%. So as of now, diesel gensets have a higher thermal efficiency than equivalent natural gas generator sets. The capital cost of diesel generator sets in dollars per megawatt is much, much lower than that for comparable natural gas units, and in many cases, it could be as low as half of that for natural gas units. This is not the operational cost, but this is basically the purchasing cost of this equipment and the packaging of these units. Fuel availability advantages are also make diesel a better solution for standby applications. This is required by many authorities having jurisdictions for emergency applications. They need on-site fuel storage, and many inspectors will not accept natural gas gensets as the emergency power supply system. Higher power density footprint than natural gas generator sets is also expected with diesel generators. They're smaller. For example, for a 2 megawatt generator, a diesel generator, it's going to take less space, it's going to be lighter than equivalent 2 megawatt generator natural gas genset. The expected life of diesel engines is longer than natural gas for low range kilowatts and under 200 kilowatt size ranges. So there are many advantages of diesel generators, and mainly it is the preferable source for emergency and standby applications.
Wissam, if I can just interrupt you, we've had a couple people say that they're having a hard time hearing you. If you could speak a little louder, please.
Sure. Natural gas generator sets for internal combustion selection considerations. Basically, the benefit there is no on-site fuel storage required for most non-emergency loads. The advantages are basically there when you have natural disasters where you have limited access to the site. It may be hard to refuel the diesel generator sets. Another thing is for large sites, on-site storage is limited, so it may be better to use a natural gas generator set. Natural gas also may be economical fuel, especially for non-emergency and non-standby applications. The fuel costs are the highest operational costs, especially for prime and continuous duty applications, and that's why you see natural gas gensets used for many base loading type applications and combined heat and power type applications. Higher exhaust temperature make it more suitable for cogeneration or combined heat and power applications because the thermal efficiency can approach up to 85 or 90%. And this is used mainly, increasingly with the Smart Grid Initiative and Renewable Energy Initiatives, and we'll talk about that later. It is able to combust a variety of byproducts, fuels such as landfills and digester biogas. The problem, though, is there is potential engine damage due to poor combustion, detonation, or corrosion if the engine is not designed to deal with the byproducts of the fuels used. So you have to consult with the genset manufacturer on a case-by-case basis. Even though diesel generators are known for better transient performance than natural gas generators, there are situations where, in cold climates, a natural gas generator or a spark-ignited engine may start easier and accept load sooner than a diesel engine. And it's also recommended for many cold climates where your temperature drops below 20 degrees Fahrenheit, because the fuel remains suitable regardless of the temperature, and there is no cloud point as you have in diesel fuel. So if we talk more about the transient performance of the generators, diesel, because of its high torque capabilities, is very responsive and is capable of starting and accepting full load in 10 to 15 seconds. This is required by many emergency standards, such as the National Fire Protection Association NFPA 110 standards for standby and emergency loads for level 1 systems. For those life safety and critical loads, you need to recover from a voltage drop and a frequency drop within 10 seconds from the moment of power interruption. And this also applies to many legally required loads, such as those used in public facilities. The problem with gas gensets is that it may take up to 2 minutes in some cases to recover to nominal frequency and voltage, and it may not be able to accept full load. There are improvements now in natural gas, and it used to take about 1 to 2 minutes to get there, but now we are seeing improvements as they can start and accept the load and recover to nominal frequency and voltage within 30 seconds, but it's still much higher and worse than diesel generators. This makes diesel generators the preferable choice for standby and emergency applications. When it comes to emissions output, in general, for the same kilowatt output, a diesel engine has lower emissions of unburned total hydrocarbons and carbon monoxide, and natural gas has lower NOx and PM output. However, with the introduction of the EPA and SPS, or New Source Performance Standards, and now in 2011 we're going to have Tier 4 interim requirements for non-emergency and non-road applications, the stationary internal combustion engine will need after-treatment devices when used diesel for these type applications, which will help reduce the NOx and particulate matter emissions output and make it comparable to the natural gas. So what you end up with is the high torque capability of diesel and all the advantages of diesel generator sets, lower hydrocarbon and carbon monoxide, and acceptable NOx and PM emissions comparable to those of natural gas. Therefore, I would say if reducing emissions is the key objective, applying after-treatment devices to the diesel engine exhaust seems to be a more economical and reliable solution than natural gas, especially for standby applications. If we talk about market trends and future opportunities for diesel generator sets, we see that there are new developments of diesel engines that will reduce the size and weight of diesel engines while increasing their power, reliability, fuel economy, and improve their emissions. So you will get the same output with a smaller generator set or a smaller engine. The other future opportunity that I see a lot of growth in, DC generators and variable speed diesel engines. We expect those to double their market share for certain commercial applications such as telecommunications and consumer markets such as recreational vehicles, RVs, and marine over the next 5 years. However, this applies more to low-range and smaller diesel engines and still does not apply to high-horsepower diesel engines. the future smart grid initiatives will increase the role of distributed generation, which will create a sizable North American prime power market. I'm involved in many smart grid codes and standards committees, and I believe that the centralized grid structure is we're gonna move basically from that type structure to a microgrid structure. So we're gonna see the prime market increasing. As of now, 90% of the generators that market in North America is mainly standby, but I do believe that that will change over the next 5 to 10 years and open the door for more peak shaving, demand response. You may see more CHP applications, and I believe that that will change the market structure, especially in the next 5 to 10 years. Data centers and large industrial applications are also the main factor driving the demand for super large generator sets. So most generator set manufacturers now have generator sets up to 2 or 2.5 megawatt gen sets. Some have up to 3 megawatt gen sets. I think that the larger motors that they are using and the larger pumps they're using in water treatment plants and in data center applications will drive generator set sizes to go up to the 3 or 4 megawatt size over the next few years. With that, thank you very much, and I'm open for questions in the following Q&A session.
Great. Thank you very much, Wissam. And thank you to all three of our presenters. We do have a few questions that have been submitted, and so we will go through some of these. Certainly, folks, please continue to feel free to submit questions as we're continuing along here. The first question, I guess, refer to Melanie, because I believe it's with regards to the Rice NESHAP rule. The question was related to emergency engines that are unattended, and the question was, how are hours for those recorded? Melanie, if you're on, I think you're still muted. Okay. Well, we're going to wait. Okay, Melanie?
You got me now?
Yes.
Okay. Sorry about that. So they should be recorded through the hour meter. That's why an hour meter is required to be installed on the engine.
Okay. Another question with regards to the NESHAP price was with regards to emergency engines. Someone saying that they thought emergency engines were exempt and that the Rice rule was just for non-emergency.
That's not correct. The only, for some emergency engines, like, for example, greater than 500 horsepower at a major source existing, they're not exempt from the rule, but they don't have to meet any requirements under the rule. For emergency that are less than 500 horsepower, emergency of any size at area sources, like, for example, I mentioned the residential, institutional, commercial facilities, those are exempt, but not all emergency engines would be exempt from the rule.
Okay. Another question from Melanie. We might as well take some of these, all that we've gotten on the NESHAP rule. There's a question, I'll read here. Aren't four-stroke lean burn engines at major sources down to 250 horsepower regulated like other sources down to 500 horsepower?
That is correct for new four-stroke lean burn, which would be the spark ignition engines. I don't think I really touched on those requirements, but yeah, that is correct for the new four-stroke lean burns from 250 to 500.
Okay, so it's just that was not that's a different point than what you were addressing. Is that correct?
That's right. Yes.
Okay. Another one here, and let me just read it for you. For the 50 hours of non-emergency runtime allowed for emergency stationary engines, what would be an example of such a runtime if they are not allowed to be run as part of a peak shave application? For example, would a storm avoidance scenario be permitted?
You're talking about like say there's a storm coming, and so you want to turn on, if you're talking about something like, storm is forecast and you want to turn on your engine so that you don't lose power, yes, that would be something that could be part of that 50 hours for non-emergency operations.
Okay. Mark, a couple for you with regards to the OTC model rule. There's concern expressed about the non-emergency standard in the rule, which could force an engine with SCR and DPFs to reduce their limits, and that this could be a problem with engines with certified aftertreatment. Can you address that?
Just to clarify, is the question more related to meeting them even with them, or meeting an alternate standard than what the EPA and SPS would require?
I can just, and if somebody who submitted that wants to address further, the question was just the concern, or I guess the way that, the current non-emergency standards are stated, that it's, problematic from this standpoint of forcing an engine with SCR and DPFs to reduce their limits.
Well, the one thing that I can say is that, again, with I can only assume that maybe the emission standard question is related to the standards for a new non-emergency generators. As I mentioned in the presentation, those relate to the most stringent Tier 4 non-road standards. Tier 4 non-road, of course, are related to compression ignition. We require the most stringent in order to get the most emission reductions. States do have, of course, the leeway to require emission standards that do go beyond any sort of federal requirement. States cannot be any less stringent, but we can, of course, be more stringent. As the OTC model rule, we decided to go with the most stringent Tier 4 requirement, so in some cases it is a little more stringent depending on the power range. And one other thing to point out as a follow-up to that, again, as a model rule, it's truly just that. It's a model rule to give states guidance on a sort of structure in which they can adopt, but they're in no means bound to adopt the exact language as it appears in the model rule. They can tweak different requirements, they can tweak different standards, they can add or delete sections as necessary, but as a model rule in the OTC development, we try to get the most agreed upon requirements all together from the get-go that most states would be able to agree on.
So the model rule as it is now, this gets to another question. So it is more stringent than the federal government's NSPS?
Only in the sense that the Tier 4 non-road rules, they apply by various power ranges. I can't think of exactly what the different power ranges are. They are broken off in horsepower or kilowatt sizes of the engines. The standards that were listed are one specific power range, which is the most common range and the most specific and most stringent of the different power ranges. It's no more stringent, as in it's not more stringent than what's listed. It's just the most stringent of the different power ranges.
I understand. Okay. All right. Great. Another concern about differences between the OTC model rule and EPA is the different definitions of emergency. Could you speak to, again, what those differences are and why OTC went with a different definition rather than the EPA one?
Yes, I can. Historically, in EPA regulations, both the NESHAP as well as the NSPSs, they had specifically stated that emergency conditions did not include any sort of peak shaving, no sort of non-emergency use was allowed, no sort of financial agreement was to be allowed for any sort of emergency engine. It's just been within the most recent promulgations of the NESHAP, as well as the NSPS proposals that occurred earlier this year, that EPA is proposing and now requesting comments on the allowance of an emergency engine to operate for up to 15 hours per year of emergency demand response. As part of the OTC model rule, we definitely debated upon this specific issue very heavily. Ultimately, it was decided to leave it in there as an emergency being power outage as the most simple explanation. We spoke with the various independent system operators in the Northeast, both ISO New England, New York ISO, as well as PJM, to learn more about their demand response programs, their emergency demand response. One interesting thing to note was that with I believe it was the New York ISO, they call upon a voltage reduction at the same time they implement emergency demand response. The OTC committee decided that seems to be very much in line with the current definition and did not see a true need to change the definition much away from power outage as well as the voltage reduction. By implementing a voltage reduction at the same time in their demand or specifically emergency demand response program, that is an allowable emergency condition. In the most recent draft and final draft of the model rule, we did include, as I showed on the presentation, an allowance for a state to include specific language to tailor the definition of emergency related to their local ISO's specific program. So it does allow each individual state the leeway if they wanted to deviate in any way from that.
Okay. Another question is with regards to credits. I believe, Mark, you were talking about credits, and the question was whether credits are allowed by EPA.
These are not necessarily allowable credits that someone can pay into to reduce. These are more or less mathematical credits. Say, for example, I'll back up and say the one credit allowance that I said was generating a non-emitting resource such as solar or wind. And the credit that would be available there would be if for example, a 1 megawatt generator was operating with alongside a 100 kilowatt wind turbine. The combined total electricity capacity of the two would be 1.1 megawatts. Therefore, the emissions from the generator alone could be applied to the 1.1 total capacity being generated as opposed to the individual 1 megawatt of the generator alone. Basically kind of receiving a credit without it being say a cap and trade credit where someone pays into a fund to emit more. Similarly with the CHP, they're just taking a thermal credit, as in by using the thermal energy and combined heat and power system, they can add it into their overall capacity to get a reduced overall emission standard. And again, the whole point of this is if a generator had to meet, for example, the 4 pounds per megawatt hour NOx limit, one of these three methods could be utilized if they were just above, say, maybe 4.1 or 4.2 pounds per megawatt hour. These methods could be utilized to help them get a little bit further in emissions without having to install further controls.
Okay, great, thank you. Another question here. For a diesel engine, is there a recommended minimum stack temperature during exercising to prevent wet stacking? I don't know, Wissam, is that maybe something you might take?
Yes. Well, there isn't a rule of thumb that you can apply. It really depends on the engine and the size of the engine. You should consult with the genset and engine manufacturer for that, but I can tell you that the rule of thumb is to keep a minimum of 30% load on the engine. If you keep a minimum of 30% average load on the engine, that will basically reach the temperature, the desired temperature for the exhaust to prevent wet stacking and carboning.
Okay. Great. There's one other here. I don't know if it's asking for a clarification between maintenance versus power outages. I don't know if that's related to an emergency definition, or I'm not sure about that question. We've seemed to have gone through any of the other most of the questions that we've received. Wissam, let me ask you one additional one, because we've heard about certainly as there's more attention to renewable energy and wind power and wind turbines and solar energy, and a lot of these new renewable sources need to have or have backup power as well, emergency power. And wonder if you could just speak generally to that and kind of that market and relative to diesel and natural gas.
Well, I can tell you I see both diesel and natural gas being used in hybrid solutions with solar or wind, especially for low range and small consumer and commercial markets like telecommunications. I can say that it's more popular to see diesel generators. However, I've seen DC gensets driven by natural gas applied in telecom applications. I think that we will see more hybrid solutions in the next 5 to 10 years combining the reliable generators with the renewable energy sources such as wind and solar. So I think this hybrid solution will continue. I think we will also see variable speed generators, AC, combined with some of these renewable energy sources.
Okay.
I had one more thing I wanted to clarify when talking about thermal efficiencies. So the thermal efficiencies of diesel gensets are better mainly for low range. A lot of the high horsepower gas gensets have comparable thermal efficiencies to diesel high horsepower engines. And the other thing regarding the starting time or from the moment of accepting load and recovering to voltage and frequency, the 2-minute or 1-minute rule for gas really apply only to high horsepower. You can meet the 10-second rule with the small low-range gas generator sets. I know we sell up to 150 kilowatt gensets that can meet the 10-second rule. So this really more applies to commercial and large industrial applications.
Okay, great. Thank you for that clarification. I think with that then, seeing no other questions, that we will conclude our session for today, and I want to thank our speakers and certainly all of our audience members for your participation. Again, the presentations and the full recorded version of today's webinar will be posted on the DTF website within the next 24 to 48 hours. And presentations from Tuesday's webinar, if you are interested in those, are already posted and can be obtained at www.dieselforum.org. With that, I want to thank you very much for your time and attention today, and I want to wish all of you a warm and safe and happy holiday season. Thank you so much, and this concludes our presentation for today.
Thank you.